SpaceX is building a propellant transfer system in orbit that would fundamentally change the economics and capability of deep space exploration. And it is the single most critical technology standing between humanity and a permanent presence beyond Earth orbit. The core problem with sending humans or large payloads to the Moon, Mars, or anywhere deep in the solar system is propellant mass. Rocket propellant is extraordinarily heavy, and the more propellant you need to carry, the heavier the vehicle, which means you need even more propellant to lift that additional mass. This exponential relationship, captured in the Tsiolkovsky rocket equation, is the fundamental constraint of chemical rocketry. It is the reason that sending a few kilograms to Mars requires thousands of kilograms of propellant on the launch pad. The solution that aerospace engineers have understood theoretically for decades is in-space propellant transfer, launching propellant separately and transferring it to a spacecraft already in orbit, effectively building a refueling infrastructure in space, the same way maritime navigation built refueling infrastructure in ports. SpaceX is building this infrastructure. The system is called the Propellant Transfer Demonstration, and it is a core component of the Starship architecture that NASA has contracted SpaceX to deliver as the Human Landing System for the Artemis lunar program. The specific requirement, as defined in SpaceX's contract with NASA, involves demonstrating the transfer of approximately 10 metric tons of cryogenic propellant between two Starship vehicles in orbit. This sounds like a technical milestone. It is actually an architecture-defining event for the future of space exploration. Starship uses liquid oxygen and liquid methane as propellants. Both are cryogenic. They must be stored at extremely low temperatures, liquid oxygen at approximately -183 degrees Celsius and liquid methane at approximately -162 degrees Celsius. Managing cryogenic fluids in the microgravity and thermal environment of Earth orbit is significantly more complex than managing them on the ground. In microgravity, liquid and gas phases of cryogenic propellants do not separate the way they do on Earth under gravity. The liquid does not sink to the bottom of the tank, and the gas does not rise to the top. This creates challenges for propellant settling, for transfer pumping, and for venting, all of which must be solved to transfer propellant reliably between spacecraft. The SpaceX approach to settling propellants in microgravity involves using small amounts of thrust to gently accelerate the vehicle, which causes the propellant to settle toward the back of the tank under the artificial acceleration, essentially creating a small artificial gravity in the direction of thrust. This ullage burn technique is established in rocket engineering, but applying it at the scale of Starship, which carries hundreds of tons of propellant, and managing the thermal conditions that cause boil-off during orbital storage are engineering challenges at the frontier of what has been demonstrated. The NASA Artemis architecture requires multiple Starship propellant tanker flights to fill a depot or directly fuel a Human Landing System vehicle before it can make the lunar journey. Early estimates from SpaceX indicated that between 8 and 17 tanker launches may be required to fully fuel a single Starship for the Earth-to-Moon trajectory, depending on the mission architecture and the maturity of the propellant transfer and storage systems. NASA's Inspector General and Government Accountability Office have flagged the propellant transfer demonstration as one of the highest-risk schedule items in the Artemis program, specifically because it represents a technology that has never been demonstrated at the required scale in orbit. The broader strategic significance of orbital propellant transfer goes beyond Artemis. If SpaceX demonstrates reliable, large-scale cryogenic propellant transfer in orbit, the economics of deep space change fundamentally. A propellant depot in low Earth orbit would allow any spacecraft to launch without the full propellant needed for its entire mission. It would launch to the depot, refuel, and then proceed. The same architecture could be applied with propellant sourced from the lunar surface. Water ice at the South Pole electrolyzes into liquid hydrogen and liquid oxygen, creating a cislunar propellant economy where fuel extracted from the Moon reduces the cost of going deeper into the solar system. The Starpipe concept, the colloquial term being used to describe SpaceX's orbital refueling pipeline, is not just a technical demonstration. It is the foundational infrastructure of any serious long-term human expansion into the solar system. The first dedicated propellant transfer test flights using Starship hardware are part of the development roadmap SpaceX and NASA are executing, with demonstrations planned before any crewed Artemis lunar landing can proceed. The demonstration requirements include transferring propellant between two spacecraft in orbit, maintaining cryogenic temperatures during extended orbital storage, which requires active or passive thermal management to minimize boil-off, and demonstrating the full end-to-end sequence from transfer to loading of a spacecraft destined for a specific mission. The challenge is not simply technical, it is also schedule critical. The Artemis program's crewed lunar landing timeline depends on this demonstration being successful before a crewed human landing system mission can be attempted. Every delay in demonstrating orbital propellant transfer directly translates to delay in the crewed lunar landing, and the schedule has already experienced significant compression from the original targets. What SpaceX is building with Starpipe is the orbital equivalent of a gas station. Infrastructure so mundane in concept and so revolutionary in practice that its success would mark the transition of space exploration from a destination-by-destination endeavor to a continuous, logistically sustained human presence in the solar system. So here is the question I want to leave you with. Orbital propellant transfer is the single technology most critical to sustainable human expansion beyond Earth. It has never been demonstrated at the scale required for crewed deep space missions, and the entire Artemis lunar landing timeline depends on it being proven before astronauts fly. If this technology works exactly as planned, what do you think the state of human presence in the solar system looks like in 30 years? And if it encounters fundamental technical obstacles, what is the realistic alternative? Drop your answer below. And if this quality of real space engineering science is what you want consistently, follow right now, because this is exactly the standard we bring every single time.